So, welcome back. In this lecture, we are going to start the solution of partial differential equations. If you remember, in the last lecture, we have given introduction to the partial differential equation, where we have seen that the general second order linear PDE, what is the form, and how we can classify into three types, and we can generate the wave equation, Laplace equation and heat equation. So, in this lecture, we are going to study at first that how to find out the solution of those PDE using the Laplace transform. Now, whenever a problem is given to us, whether I can use Laplace transform or I can use Fourier transform or not to solve the problem, that we have to decide at first. So, here we are going to the application of Laplace transform in solving the PDE. So, first thing is criteria for choosing a Laplace transform, that is whether Laplace transform is applicable or not, and as you have seen in the functions, that is wave function, heat function, Laplace transform, Laplace function, you have the more than one independent variables. Say it is x t or y is a function of x t or something like that, u is a function of x and y. So, with respect to which variable you will take the transform, that you have to choose. So, since we are going through the Laplace transform, first let us discuss the criteria for choosing the Laplace transform. The first one you have to see is both the independent variables or at least one of the independent variables should have range from 0 to infinity. So, please note this one, the variables, independent variables with which you are working, the range should be or must be from 0 to infinity. Out of two, at least one should have this range, because if for both the range is minus infinity to infinity, I cannot use Laplace transform, because if you remember, Laplace transform has been defined in 0 to infinity only. Therefore, you cannot use the Laplace transform if the independent variable is varying from minus infinity to infinity. So, very first thing you have to check whether both the independent variable or at least one independent variable varies from 0 to infinity or not. Next is, if both the variables have range from 0 to infinity, you can apply Laplace transform with respect to any one of the variables, quite obviously with respect to any one of the variables. If only one variable has the range from 0 to infinity, then you apply Laplace transform with respect to that variable only. So, number 4 is important, that appropriate conditions must be specified as the lower limit of the variable. Please note this, appropriate initial condition must be specified at the lower limit of the variable which has the range from 0 to infinity. This I will explain in the next slide itself, that what do we mean by appropriate initial condition. Because whenever you are taking Laplace transform of second order derivative, whether it is partial or ordinary derivative, some constant values are coming, and if I do not know the values of those constants, then it becomes difficult for us to solve the problem. So, therefore, the fourth criteria is very important. Please note then that whenever I want to apply Laplace transform to solve one PDE, first thing I have to check whether the independent variables are varying from 0 to infinity or not, or at least one independent variable is varying from 0 to infinity or not. Please note that if it is varying, not varying from 0 to infinity, I cannot use the Laplace transform. So, these are the criteria. Now, if y x t is a function of x and t, and suppose t has the range from 0 to infinity, I am not talking about x, I know that the time usually always will be from 0 to infinity. Then we have not done this thing earlier, because whatever we have done the derivatives only, not partial derivatives. Laplace transform of derivatives we have done earlier, if you remember, and by that way we have solved the first order ordinary differential equations also. So, now we are giving some formulas. One is, because this is required, number A is Laplace transform of del y del t equals s into y bar x s minus y of x 0, where y bar is nothing but Laplace transform of y. This y of x 0, that means this is a constant term basically. Whatever initial condition I was talking about in point number 4 in the earlier slide, initial condition, this is one of the initial condition. At t equals 0, the value of the function should be known to us. Otherwise, I cannot evaluate or I cannot use Laplace transform. Please note this one. Similarly, the Laplace transform of second order partial derivative, that is Laplace transform of del 2y del t square equals s y bar x s minus s y x 0 minus y t x 0. So, whenever I am taking the Laplace transform of second order partial derivatives, I need to know the value of the function y and the value of the derivative of the function y, that is y t at t equals 0. If I do not know these two values, I cannot proceed, or in other sense, if these two values are not known to us, we cannot use the Laplace transform for solving one partial differential equation. So, the second property is Laplace transform of del 2y del t square equals s y bar x s minus s y x 0 minus y t x 0, where y bar is nothing but Laplace transform of x, Laplace transform of y. That is the reason y bar is a function of x and s. Laplace transform of del y del x is nothing but dy bar dx, and similarly Laplace transform of del 2y del x square, this equals d2y bar dx square. Please note this thing, that Laplace transform of del y del x, y is a function of x and t, and you are taking Laplace transform with respect to t. So, for the other variable, simply Laplace transform of del y del x is dy bar dx, where y bar is Laplace transform of y, and number 4, the Laplace transform of del 2y del x square equal to d square y bar dx square, but Laplace transform of del y del t and Laplace transform of del 2y del t square can be obtained by this formula. So, first let us see the proofs of this one. Proofs of first one, that is Laplace transform of del y del t. From the definition you can write down 0 to infinity e power minus s t into del y del t, sorry not u, this you can write down e power minus s t into del y del t into dt. So, if I use the integration by parts on this particular equation, you will obtain e power minus s t into del y del t. This will be a function of x and t, limiting value will be from 0 to infinity, plus s will come here after integration by parts 0 to infinity e power minus s t into y of x t dt. This value, first part will be 0, second part will be minus y of x 0, whenever you are putting the lower limit at t equals 0, plus s into, what is this? This is, you see, 0 to infinity e power minus s t into y t x t, and this is nothing but y bar x s, means the Laplace transform of y x t. This is the from definition, this we can tell 0 to infinity e power minus s t into y of x t dt. Therefore, this is nothing but y bar x s, and so you can write down s into y bar x s minus y of x 0. So, which completes the proof of the first part. So, I think it is clear. that Laplace transform of del y del t equals s y bar x s minus y of x 0. So, let us see here your y proof of the first one, as I told, Laplace transform of del y del t is 0 to infinity e power minus s t into del y del t dt, which by integration by parts you can write down, where the second integral is nothing but the Laplace transform of y t. So, if I evaluate put the limit on the first part for infinity, the value will be 0. At t equals 0, it becomes minus y x 0 plus x y bar x s. So, that I can write it s y bar x s minus y of x 0. This completes the proof of the first one. Let us see the proof of the b part, that is Laplace transform of del 2 y del t square. This equals, I can write down Laplace transform of del v del t, say, where you can write down del y del t, this is equals v. If I substitute v equals del y del t, then Laplace transform of del 2 u del t square equals, we can write down Laplace transform of del v del t, and from the earlier property this equals, we can write down s into Laplace transform of v minus b of x 0. So, this equals, I can write down s into Laplace transform of v, that is Laplace transform of del y del t. Again you can put the value here, so that s y bar x s minus y of x 0 minus b of x 0, b is nothing but y t. So, we can write down y t x 0. So, your v is nothing but y t. So, basically your v was del y del t. So, Laplace transform of del y del t, again you are using the earlier formula and you are obtaining it. So, that this equals s square into y bar x s, sorry, this will be s square into y bar x s minus s y x 0 minus your y t of x 0. So, this completes the proof of the second part, that is this one, s square into y bar x s minus s y x 0 minus y t x 0. So, if you see the proof of the next part, on the same way we are writing it as Laplace transform of del v del t, where del y del t, this is equals to v, and in the next part you are putting the value of del v del t. Laplace transform of del v del t is s into Laplace transform of L v minus b x 0. If you put s into this thing will come, and this will be, oh, that is a mistake, this will be s square into y bar x 0. Please note this one, this will be s into y bar x 0 minus this thing, this part will become s square into y bar x s minus s y x 0 minus y t x 0. So, this completes the proof of the second part. For the third one, that is C part, Laplace, these are very easy. Laplace transform of del y del x, this is equals, you can write down 0 to infinity e power minus s t into del y del x into dt, you can write down, and del y del x. So, here it is a function e power s t is function of t only. So, that this del x I can bring outside as d dx, because this will be simply a function of s. So, d dx into 0 to infinity e power minus s t into y into dt, and this is nothing but again 0 to infinity e power minus s t into y dt, this is nothing but Laplace transform of y or y bar. So, that you can write down this equals d y bar into dx. So, you can write down this thing as d y bar dx. Therefore, Laplace transform of del y del x is equals to, directly you can write down dy bar dx, and the last one is Laplace transform of the del 2y del x square. This is equals, again I can write down Laplace transform of say del capital U del x, which is equals to where del y del x equals capital U, you can assume. This equals, you can write down d dx of Laplace transform of u. So that this equals, you can write down d dx of Laplace transform of u is del y del x. And once I am taking the Laplace transform of this, Laplace transform of del y del x, already we have obtained dy bar dx. So, using this one, you can write down d2 y bar dx square. So, this is equals to Laplace transform of del 2y del x square. This is equals to d2 y bar dx square. So, all these four will be required for us. Let us see the next part, number 3 also here. Your Laplace transform of del y del x, this is equals to 0 to infinity e power minus st del y del x into dt. Now, since it is a function of y and x, so ddx can bring out ddx can come outside. So, I can write it ddx of 0 to infinity e power minus st into y dt, and this is nothing but y bar. So, that I obtain my required result. And the fourth part is Laplace transform of del 2y del x square. This I can write down Laplace transform of del u del x, where u is del y del x. This d dx I can bring outside. So, that d dx of Laplace transform of u, and Laplace transform of u means del y del x, u is del y del x, and from the earlier property Laplace transform of del y del x is nothing but dy bar dx. So, that it will become, again there is a mistake here, this one again will be d2 y bar dx square. Please note this one, this will be d2 y bar dx square. So, this is y bar will come here, please note this, make changes, d2 y bar dx square will come over here. So, this completes the proof of these four things. For evaluation of these partial derivatives with respect to Laplace transform, I have to use these four. Now, let us see the first application. I want to solve this PDE. I will take either heat equation or wave equation or Laplace equation one by one. The first equation I am taking as del u del t equals k del 2 u del x square. Both x and t are greater than 0. It is given that u 0 t equals f t whenever t greater than 0, and u x 0 that is equals 0 whenever x is greater than 0. So, both are given to us, that is the function u is a function of two variables x and t. What you are doing here, the equation is del u del t equals k del 2 u del x square. Your u 0 t equals function of t is given to us whenever t greater than 0, and at t equals 0 u x 0 equals 0 whenever x greater than 0. Let us see the solution process of this. So, at first I have to decide with respect to which variable I should take the Laplace transform. Your equation is this one, del u del t equals k del 2 u del x square, where your x is greater than 0 and your t is greater than 0. This is given to us, and the initial condition is also given, that is u 0 t equals f t is given and u x 0 this is equals 0. Of course, for both cases u 0 t equals f t for t greater than 0 and u x 0 equals 0 for x greater than 0. So, here both the variables at the has the range from 0 to infinity, initial conditions are given. So, what I am doing? I am take Laplace transform on both sides with respect to t. Please note this, for every solution I have to tell very clearly with respect to which variable I want to take the Laplace transform. This is very important to us. Please note this thing. So, Laplace transform of del u del t, this is equals to k into Laplace transform of del 2 u del x square. And we have the formulas effectively, that Laplace transform of del 2 u del x square, this is there. We are taking the Laplace transform on both sides with respect to t, and I can write down Laplace transform of del u del t equals k into Laplace transform of del u del x square. Now, you know that Laplace transform of del 2 u, just I am writing, afterwards you can remember it. Already we have done, this is equals to s square into y bar x s, sorry, this is s square into y bar x s minus y s into y x 0 minus y t x 0. So, once I am doing this thing y t x 0, so you will obtain this as s into u bar x s minus u x 0, sorry, this is del u del t I am doing it. So, for del u del t it is s u bar x s, I have written it for the del 2 u del t square, whereas for the other one it is s into u bar x s minus u x 0, and because you are doing the Laplace, taking Laplace transform of with respect to t, not with respect to s. So, with respect to t, if you take Laplace transform of del u del t will be equals to s u bar x s minus u x 0, and on the right side Laplace transform of del 2 u del x square, this is simply your will be d 2 u bar d x square, where your u bar is nothing but Laplace transform of u x t, Laplace transform of u x t. So, taking Laplace transform on both sides of the given equation, you are making Laplace transform of del u del t is s u bar x s minus u x 0 equals k into del 2 u bar del x square, where u bar is this. You know the value of u x 0, u x 0 is given to us. So, that u x 0 is equals to 0 from the given condition, you substitute it. So, you can write down d 2 u bar d x square minus s by k into u bar equals 0. This is an ordinary differential equation with your values are m square minus s by k equals 0. So, that m will be plus minus s by k, and I can find out the solution of this as. So, your equation was this thing d 2 u bar d x square minus s by k into u bar, this is equals to 0. From here you can directly write down u bar x s, this is equal some constant a into e power root over s by k into x plus b into e power minus root over s by k into x, where since you are getting it of the form of from here the function, you can write down m square minus s by k equals 0. So, that m square is s by k, m will take two values s by k and plus s by k and minus s by k, and from there you are writing the values of these as u bar x s equals a e power root over s by k into x plus b e power minus root over s by k into x. What is your next job? Your next job is to find the values of a and b. Now, your uxt, this approaches 0 as x approaches infinity. From the properties, initial value and final value theorems, as x approaches infinity, your uxt approaches 0. So that you can say that u bar xs will approach 0 as s approaches infinity. From the properties I can tell. So, from here one condition I am taking uxt approaches 0 as x approaches 0, because ux0 was 0 whenever x greater than 0. From there I am saying uxt approaches 0 as x approaches infinity. If I take the Laplace transform, then u bar xs will be approaching 0 whenever x approaches infinity. Therefore, from the given equation, if I take the equation 1 here, from the equation 1 what you will obtain? If I substitute this approaches 0 as x approaches infinity, so this term will be vanishing and you will obtain your a as 0 from here. So, one value of the constant is 0, so that when you are obtaining a equals 0. Also, you know this thing, when x equals 0, u equals some function of t is given to us. So, from here you can tell that u bar 0 s, this is equals to 0 to infinity f t into e power minus s t dt, and this is nothing but f bar s. So, for the second one what you are doing, u equals f t is known to us. I am taking the Laplace transform on both sides of this equation. So, if I take Laplace transform of u, this will be u bar 0 s at x equals 0, and this is 0 to infinity Laplace transform of f t is nothing but 0 to infinity f t e power minus s t dt, and which is equals f bar s. If you substitute in 1 again, this will give you u bar 0 s. So, your b is nothing but f bar s you are obtaining. You will obtain from here b as x approaches 0, this term will be 0, and u bar 0 s is f bar s. So, that b equals f bar s. So, your u bar x s in equation 1, value of a is 0 and value of b is f bar s. So, that you can write down your u bar x s equals e power minus root over s by k into x into f bar s. And from here, once you obtained u bar, taking inverse Laplace transform, you can write down u x t, this is equals to Laplace inverse of minus root over s by k into x into f bar s. Since the function f t is not known to us, therefore, f bar s is also not known to us. So, Laplace inverse we cannot evaluate. We can evaluate it only the function f t was known to us. We have done a generic thing over here. So, by this way we can find the solution of the equation. Let us see quickly for this particular problem. Your Laplace, taking Laplace transform on both sides of the given equation, you are getting this. So, that Laplace transform of del u del t is s u bar x s minus u x 0 equals this. Your u x 0 is 0, and you will get this ordinary differential equation. The solution you can obtain very easily by equation 1, where a and b are constants. We have to find out the values of these two constants. Your u x t approaches 0 as x approaches infinity. This we are getting basically from this condition, that your u x 0 is 0 whenever x greater than 0. So, from here you can tell this thing, that your u x t will approach 0 as x approaches infinity, and from here you take the Laplace transform. So, u bar x s approaches 0 as s approaches infinity. So, from 1 you will get a equals 0, Also I know whenever x is 0, u equals u f t. So, u f t, if I take the Laplace transform on both sides, you will obtain u bar 0 s at x equals 0 equals 0 to infinity f t power minus s t, which is nothing but f bar s. So, if I substitute in equation 1, again I will obtain b equals f bar s. So, using the initial conditions by this way, I have to find out the values of the constants, and I obtain the values of a and b. So, I obtain u bar like this. So, that your u will be u x t will be Laplace inverse of e power minus root over s by k x into f bar s. And once I know the function f t, I can evaluate f bar s and I can find out the Laplace inverse. So, by this process we can solve the equations. In the next lectures also we will solve some other PDEs also of other types.